we are going to present you a series of videos in which we are going to discuss most important questions that are frequently asked in school exams. Hi, my name is Arun Koshish, and in this video we are going to discuss questions based on complex numbers. So these are the set of questions we are going to discuss in this video. In the first question, first of all, we solve iota raised to 18 which is equal to iota raised to 4 into 4 plus 2 which is equal to iota raised to 4 whole raised to 4 into iota square which is equal to 1 into iota square equals to minus 1. Similarly, 1 upon iota whole raised to 25 is equal to 1 upon iota raised to 25 which is equal to 1 upon iota raised to 4 into 6 plus 1 which is equal to 1 upon iota raised to 4 whole raised to 6 into iota equals to 1 upon iota. Now multiplying and dividing by iota, we get iota upon iota square which is equal to minus iota. Therefore, we get minus 1 minus iota whole cube which is equal to minus 1 cube into 1 plus iota whole cube which is equal to minus 1 into 1 plus iota whole square into 1 plus iota which is equal to minus 2 iota into 1 plus iota equals to minus 2 iota plus 2. In the next question, 1 upon 1 minus 4 iota minus 2 upon 1 plus iota equals to, taking LCM, 1 minus 4 iota into 1 plus iota equals to 1 plus iota minus 2 plus 8 iota upon 1 plus iota minus 4 iota plus 4 which is equal to minus 1 plus 9 iota whole upon 5 minus 3 iota. Therefore, we get minus 1 plus 9 iota upon 5 minus 3 iota a whole into 3 minus 4 iota upon 5 plus iota. On multiplying numerator terms, we get now we realize this by multiplying with 28 plus 10 iota numerator and denominator. We get 924 plus 330 iota plus 868 iota minus 310 upon 28 square plus 10 square which is equal to 614 plus 1198 iota upon 784 plus 100 which is equal to 614 plus 1198 iota upon 884, cancelling 2 we get 307 plus 599 iota upon 442. In this question, the numerator is 3 plus iota root 5 into 3 minus iota root 5 which is equal to 3 square plus root 5 square equals to 9 plus 5 which is equal to 14, and in the denominator root 3 terms cuts with root 3, so we get 14 upon 2 root 2 iota which is equal to 7 upon root 2 iota. Now multiplying and dividing by iota, we get 7 iota upon minus root 2, so we get minus 7 upon root 2 iota. The given expression is x minus iota y equals to under root of a minus iota b upon c minus iota d. Squaring both sides, we get x minus iota y whole square is equal to a minus iota b upon c minus iota d. Now taking conjugate on both sides, we get x minus iota y whole square conjugate equal to conjugate of the right side. This implies x plus iota y whole square equals to a plus iota b upon c plus iota d. Now multiplying the two equations, we get x minus iota y into x plus iota y whole square equals to a minus iota b upon c minus iota d times a plus iota b upon c plus iota d. So this implies x minus iota y into x plus iota y whole square equals to a square plus b square upon c square plus d square. This implies x square plus y square whole square equals to a square plus b square upon c square plus d square. We are given a plus iota b equals to x plus iota whole square upon 2x square plus 1. Taking conjugate on both sides, we get a plus iota b conjugate equals to conjugate of the right side. This implies a minus iota b equals to x minus iota whole square upon 2x square plus 1. Now these are the two equations. Multiplying both sides of the two equations, we get a plus iota b into a minus iota b equals to x plus iota whole square upon 2x square plus 1 into x minus iota whole square upon 2x square plus 1. This implies a square plus b square equals to, in denominator we get 2x square plus 1 whole square, and in numerator we take square common and then we write x plus iota to x minus iota whole square. This implies a square plus b square equals to x square plus 1 whole square upon 2x square plus 1 whole square. In this question, first of all we simplify z1 z2 upon z1 conjugate, which is equal to 2 minus iota into minus 2 plus iota upon 2 plus iota, which is equal to minus 4 plus 2 iota plus 2 iota plus 1 upon 2 plus iota equals to minus 3 plus 4 iota upon 2 plus iota. Now multiply and divide by 2 minus iota to realize it. Minus 2.5 plus 11.5 iota. Now therefore real part of z is minus 2 upon 5. Now next one is imaginary part of 1 upon z1 conjugate. 1 upon z1 conjugate is equal to 1 upon 2 minus iota is equal to 1 upon 4 plus 1 equal to 5. Therefore imaginary part of that is 0. Given x minus iota y into 3 plus 5 iota is conjugate of minus 6 minus 24 iota. Therefore 3x plus 5x iota minus 3y iota plus 5y equals to minus 6 plus 24 iota. This implies 3x plus 5y equals to minus 6, and 5x minus 3y is equal to 24, comparing real and imaginary parts. This implies x is equal to 3 and y is equal to minus 3 by solving the two equations. In this question, first of all, x plus iota y whole cube equals to x cube plus 3x square y iota plus 3x y iota whole square plus y iota whole cube using the formula of a plus b whole cube. This is equal to x cube therefore x plus iota y whole cube equals to u plus iota v implies comparing real and imaginary parts, x cube minus 3x y square equals to u and 3x square y minus y cube equals to v. This implies x common, x square minus 3y square equals to u. This implies x square minus 3y square equals to u upon x. Similarly, we have y times 3x square minus y square equals to v. This implies 3x square minus y square is equal to v upon y. Adding the two, we get 4x square minus 4y square equals to u upon x plus v upon y. Therefore, u upon x plus v upon y equals to 4 times x square minus y square. To convert minus 16 upon 1 plus iota root 3 into polar form, first of all, we realize this expression by multiplying and dividing it with the conjugate of the denominator 1 minus iota root 3. We get minus 16 times 1 minus iota root 3 upon 1 plus 3, which is equal to minus 16 times 1 minus iota root 3 upon 4. Now cancelling 4, we get minus 4 plus iota 4 root 3. Now we write its polar form as r times cos theta plus iota sin theta. Comparing real and imaginary parts, we get r cos theta equals to minus 4 and r sin theta is equal to 4 root 3. R equals to minus 4 square plus 4 root 3 whole square, which is equal to square root of 16 plus 48, which is 64, and it is equal to 8. Now r cos theta is equal to minus 4 implies cos theta is equal to minus 4 upon 8 equals to minus 1 by 2, and similarly sin theta is equal to 4 root 3 upon 8 equals to root 3 upon 2. Cos theta is negative, sin theta is positive, so theta lies in second quadrant. Therefore theta is equal to pi minus pi by 3 equals to 2 pi by 3. Therefore the required polar form is 8 times cos 2 pi by 3 plus iota sin 2 pi by 3. In this question, first of all, we write polar form of minus 1 plus iota equals to r times cos theta plus iota sin theta. Now r is equal to minus 1 square plus 1 square, which is equal to root 2. Comparing real and imaginary parts, r cos theta is equal to minus 1, r sin theta is equal to 1, implies cos theta equals to minus 1 upon root 2. and sin theta is equal to 1 upon root 2. Now theta lies in second quadrant, as cos theta is negative, sin theta is positive. So theta is equal to pi minus pi by 4. Therefore, minus 1 plus iota is equal to root 2 times cos 3 pi by 4 plus iota sin 3 pi by 4. So we put the value of minus 1 plus iota in the expression. We get root 2 times cos 3 pi by 4 plus iota sin 3 pi by 4 whole upon cos pi by 3 plus iota sin pi by 3. Now multiplying and dividing by cos pi by 3 minus iota sin pi by 3, we get root 2 times cos 3 pi by 4 cos pi by 3 minus iota times cos 3 pi by 4 sin pi by 3 plus iota times sin 3 pi by 4 cos pi by 3 plus sin 3 pi by 4 sin pi by 3 whole upon denominator is cos square pi by 3 plus sin square pi by 3, which is 1. So the expression this equals to root 2 times cos 3 pi by 4 minus pi by 3, using the formula of cos A minus B equals to cos A cos B plus sin A sin B. Similarly, iota times sin 3 pi by 4 minus, which is equal to root 2 times cos 5 pi by 12 plus iota sin 5 pi by 12, which is the required Euler form. In this question, 3 plus 2 iota sin theta upon 1 minus 2 iota sin theta is given to be purely real. By multiplying and dividing it, conjugate of the denominator 1 plus 2 iota sin theta, we get in denominator 1 plus 4 sin square theta, in numerator 3 plus 6 iota sin theta plus 2 iota sin theta minus 4 sin square. Now separating real parts and imaginary parts, we get 3 minus 4 sin square theta upon 1 plus 4 sin square theta plus 8 sin theta upon 1 plus 4 sin square theta iota. Now since the expression is purely real, therefore its imaginary part 8 sin theta upon 1 plus 4 sin square theta is 0. This implies sin theta is equal to 0. Sin theta is 0 implies theta is 0, pi, 2 pi and so on. This implies theta is equal to n pi, where n belongs to integers. In this question, alpha and beta are two different complex numbers with mod beta is equal to 1. Now mod beta equals to 1 implies mod beta square equals to 1 implies beta beta conjugate equals to 1. Now mod of beta minus alpha upon 1 minus alpha beta conjugate, here we put 1 is equal to beta beta conjugate and then take beta conjugate common from the denominator. Now cancel beta minus alpha factor from numerator and denominator. We get 1 upon mod beta conjugate, which is equal to 1 upon mod beta, and mod beta is 1. Therefore the required expression is equal to 1. In this problem, first of all we find mod of 1 minus iota is equal to under root of 1 square plus minus 1 square, which is equal to root 2. Therefore, we put the value of mod of 1 minus iota in the question. We get root 2 raised to power x equals to 2 raised to power x. This implies x by 2 equals to x. This implies x minus x by 2 equals to 0, which implies x is equal to 0. Therefore, there is no non-zero integral solution of x. In the next question, 1 plus iota upon 1 minus iota is equal to 1 plus iota upon 1 minus iota into 1 plus iota upon 1 plus iota. Realizing this expression, we get 1 plus iota whole square upon 1 plus 1, which is 2. 1 plus iota whole square is 2 iota. 2 iota upon 2 equals to iota. Therefore, iota raised to power m equals to 1. Iota raised to m equal to 1 implies m is a multiple of 4, 4, 8, so on. So the least positive integral value of m is 4.